gracias a Dios que yo también he sobrevivido hasta el final. Y bueno, pues vamos a acabar lo mejor que podamos. Entonces, bueno, el objetivo de esta última sesión es, bueno, vamos a acabar un poquito de texto. So, thank you. So the goal for this last session is that to finish a bit the things we did about tensor networks, to comment very briefly about different models of quantum computation, and show that in those models, these objects, like the spectral gap, MLSA constants, enter, so that obtaining results or techniques, I would say, to prove those bounds on those objects, on the spectral gap and the MLSA constant, could have an impact on computation. And then give a kind of final example in which many of the bricks these building blocks that we have been using come together, and you can see an example in which all these ideas really come together to show a bound on the lifetime of topological quantum memories. Okay, so that's the plan. So, okay, so since the goal is to talk about topological quantum memories, one is to talk about something which is called topological order. So topological order, okay, as many concepts in physics, I don't know if it's well defined. But there are systems that are, so there are some properties of a system that are kind of, if the system has these properties, people say it has topological order. And there are models that have all those properties, and then people, okay, these clearly have topological order. But there is not a unique definition of what topological order is. So in any case, I will not define it. I will just construct particular examples. The original ones by Kitaev in a very influential paper that is called Quantum Computation by Anions, in which he showed how the idea that with those exotic objects, one could do quantum computation. And I will explain exactly the models that appear in that paper, but with the notation or language of tensor networks. Okay, it's exactly the same objects, but I will change the language. Okay, so we start with a finite group G, and if you want, you can assume the simplest one. G is C2. Okay, for the case of C2, this is the toric code, what I'm going to define, which is by definition the paradigmatic example of topological order. And now we take UG, which is the left regular representation, which in our Ken notation is simply saying that U sub G acting on H. H is an element of the group, and then the Hilbert space, because the left regular representation, the Hilbert space in which it acts is just indexed by the group elements. So this is the index of my orthonormal basis, and now it's left regular, so this acts by left multiplication, no? So that's the representation. And in our notation of matrices, this unitary matrix can be written like that. Okay? Good. This is our bracket notation. So we are now using all the things we have been. Okay. Okay. It's clear to all of you, but it's obvious that it's a representation. And it has nice orthogonality relations. And this is trivial from the fact that this is a representation and that all objects here are traceless, which is trivial by the definition, except for the identity. Then it's clear that this is true. Okay, but one can simply compute it. So essentially, in the Hilbert-Smith scalar product, all these objects are orthonormal. Okay, normalized properly, of course, are orthonormal. Yes.
Unitary.
This is a unitary representation. Sorry? This is a unitary representation. So this is the left regular. This is a very particular one. It's this unitary representation. And it's important for me that is exactly the left regular. Okay? It's this particular representation. So I'm just defining a model. So this is one example. This is that. Okay? So now, okay, tensor networks. I'm going to define. So you can think in 1D first, if you want. But the important thing is in 2D. So now I will define this object. This is just simply, Okay, 1 over the size of the group, sum of the group, and then it's the tensor product, because I'm putting two things together, juxtaposition, so it's tensor product, of UG and UG daga. So you just, so mathematically this is what it is. So it's sum of G of UG tensor UG daga. That's it. But I write it like that. I write a matrix UG is a two-index tensor, no? A matrix has two indices. So I can represent it by a blob and two legs. The input leg and the output leg. So row and column legs. No? And this is the same. As you see, I reverse the arrows. So UG goes from left to right, UG daga goes from up to. So that's the way that the input and the output enters. Okay. And now, of course, this is, I can see it's a big blob with two legs outside, which are this and this, left and right, and one leg up, which is made out of two. So this one is these two together. Okay, that's the. Is it clear? So this is just the definition of this blob, like that. Good. Okay, one can do the same in 2 dimensions. Now, okay, it's more difficult to draw, but now you have to think how you would generalize this here. No. UG is, this UG has one arrow coming here and one going up. This UG has one arrow coming here, one up. This daga up like that, this daga down like that. Okay, so it's the analog of that object. And this defines me this blob. Okay, we didn't put all the arrows here because it would be a mess. But I think from here, I guess you can see, imagine what is the thing here. Okay. Okay, good. So this object, this blob, defines a PEPS by the picture that I put before there. It's just I put this blob everywhere in a lattice, in a torus, and this is a tensor. This is a particular state. No? So I take this particular thing here, and I create a lattice using the very same everywhere. This one defined by that everywhere. Okay? Etc. with periodic boundary conditions. Okay? Etc. And then there is a physical index going up. So this blue index I put there, this blue one. Okay, so this is the state. I can define this state for every system size. So if this is L and this is N, so this I can define for every L and N in a torus. Okay. So this object is a particular state, which is called the quantum double state, or one of those. And then, because it's a PEPS, it has a parent Hamiltonian. There is a parent Hamiltonian. Which in this case, it acts in a plaquette. So it's enough that acts in plaquettes. Okay. When I define a parent Hamiltonian, I need to define a particular region of a particular size. For this particular example, these regions are plaquettes. Okay, just plaquettes. These are P plaquette, HP tensor identity in the rest as always. Okay, and HP is just the projector, the parent Hamiltonian construction, as you remember, the projector onto the range of this gamma R matrix operator that I defined before. Okay. Okay, so then this object and the associated parent Hamiltonian are these topologically ordered models. Okay. Again, this is the tensor network view of Kita F construction. Okay, these objects are called G isometric PEPs. G is the group. Okay, and these kind of tensors that define the tensor network have a very important property, and is the fact that if I apply UG in the corresponding places, this is just left invariant, and this is obvious. No, because this is the projector onto the symmetric subspace. I have sum in all G's. If I multiply by one UH here, UH dagger here, of course, by rearranging the way I I index all the group elements, is the same object. Okay, this is clear, right? I'm just again summing over all group elements again, simply in a different order, but doesn't matter. Okay, so this tensor has an internal symmetry like that. Okay, these things are much closer to what a gauge symmetry is now. Okay, indeed, in the tensor network language, we call this a gauge symmetry. And this is really behind gauge theories, but Enrique knows a lot about it. Okay, so that's important. So this tensor has symmetries, and precisely those symmetries, the ones that are responsible for the very exotic properties of the model. So the model being so simple, I mean, as you see, there is nothing strange here. It has very strange properties. This is this topological order. So let me show you which are those properties. Okay, so first to lighten a bit the notation, instead of writing UG, I will write just G. Okay, when I write a block with G, it's just UG. Okay, so this, and of course, UG daga is G inverse because it's a representation. So this is the internal symmetry in the tensor. Okay, so that's simply because now what I'm going to do. Okay, sorry, before properties of the sparse Hamiltonian. Okay, this is for 1D. For 2D, it's kind of the analog, but painting in 2D is a mess. So I will do the paintings in 1D. So the Sparse Hamiltonian is made of commuting terms. That's a very strong property. So all the terms in the Sparse Hamiltonian commute with each other. Okay, this doesn't mean at all that the model is classical. Okay, at all. Okay. Moreover, the terms in the Sparse Hamiltonian has a nice description in terms of the tensors themselves, and the description is just that. So A is the tensor. This the one that appears here. This tensor is A. Again, the same is true for 2D, but let me do 1D. And then I can describe the Sparse Hamiltonian as follows. I call Q to this object. This Q is clearly self-adjoint because it's something daga. That's clear. It's a projector. This is not difficult to see. I mean, if I have time, I can do that. I mean, maybe I can prove one of the things because all of them have essentially the same ideas behind the proof, at least those things here. The range of the projector is this G2. G2, remember that is exactly what you want to be the kernel of the Sparse Hamiltonian. And it stabilizes the elements in G2. Okay, these things together show that the Sparse Hamiltonian, by definition of Sparse Hamiltonian, is exactly identity minus Q. Or minus Q simply, but okay, if you want the Sparse Hamiltonian construction, that is a projector identity minus Q. Okay, so there's a nice way to write the Sparse Hamiltonian in terms of the tensors themselves. And the tensor, I mean, it's made of, and they commute. So the commutation, so this is the fact that they commute. So I can even do the proof of that, so that you see that all these things I'm saying now are very easy. So I will do that, the proof of that, but the other things are equally easy. Okay, so I will prove that. So they commute. So just to prove something. So nothing of this is hard. Okay, so this is the term. Okay. Okay, this is the Hamiltonian. So I'm in one dimension. I have Hamiltonian 1, Hamiltonian acts on size 1, 3 here. This one. 1, 2, sorry, and the other on side 2, 3 here. No? And I have to prove that acting first with the 2, 3, I'm assuming that I'm acting in that direction. Acting first with the 2, 3 and then with the 1, 2 is the same as vice versa. Okay. Okay, so the key thing is that because this object this is just the sum in G of UG tensor UG daga 1 over G is a self-adjoint projector. If I do this and then the adjoint is the same as doing it itself, So this is equal to this, equal to that. So this is equal to, now with my notation, G, I forgot the direction of the arrows, doesn't matter, G minus 1. Okay? Okay, simply because this is equal to that, because this is a self-adjoint projector. And this is the adjoint of that. So this is that. So now I look that this appears here. Okay? So I will change this by this, because it's the same. Okay? So let me do it next door here. Okay, I can do this. Like that. And here I have G minus 1, and a summing G. Okay? Okay? This is equal to that. Okay? And 1 over G, of course. And now I use the key property, which is the internal symmetry of the tensor. That's the key property, as I said. This internal symmetry. That for 1D tensors, of course, this is the 2D version. For 1D tensor, the symmetry is that G minus 1 is that, or what, if you want the same, that G equals G. So that the G passed to the other side. This is called the pulling through condition, and by a reason, because you can pull through the G from one side to the other. Okay? And I do that. So I take this G, and I pass it from here to here. And so on and so forth, from here to here. From here to here, and it touches G minus 1, and it cancels. Suddenly, it doesn't depend on G. So, of course, this and this 1 over G cancel too. And I have that. Okay? And now, of course, I rearrange the lines. And this is exactly this. Okay? And of course, I can do the same at the other side, and I get exactly, of course, the same diagram. So they commute. Okay, and that's it. As simple as that. Okay? And all the other properties I wrote before have an equally simple proof. Simple proof. So it's same type of things. Okay? Good. Okay, so now which are the strange properties now for the 2D case? So now take two different group elements that they commute. Okay, the group doesn't need to be abelian, but these two group elements should commute. And for each pair of group elements that commute between themselves, I write a particular state, which is the following. This is the original state I had, but now I will enrich it. Okay, I take I put an H, UH, in a string around the torus. Okay, remember we have periodic boundary condition. This is a string around the torus. So this is a string around the torus. Okay, of H's. And I put a string of G's in the other direction. Okay. Of G's, like that. Okay. So let's see what happens with those strings. So first of all, I will write it in this picture. So I write here, let's say I have a G here, G and G. And I will use again my gauge symmetry. Gauge symmetry, in that case, I have is that GG, G minus 1, G minus 1 is nothing. Okay. So now what I can do is, of course, for instance, this G here, I can pass it to these three sides and put here a okay, I don't know exactly where G minus 1s are now, but okay, let's say G minus 1 here and G here. I do the same with this G. G here, G minus 1 here. I do the same with this G. G here, G minus 1 here, G here. And you see that everything here cancels. G minus 1, G minus 1. Oh, I forgot. A G here, G minus 1. So all these things cancel. And then this, I can pass this line to the next one. And everything is an equality. So what I mean is that these strings of G's are not localized in any particular position. So the state with the string here and the state with the string here is the same state, the same object. Okay? So this thing can be freely moved, and also deformed, as we said, can also deform like that, by using just this symmetry. We can do the same with the H. And the key thing why they commute is that in order to deform the two of them simultaneously, we need to pass H through G at some point, and we need the two elements to commute. Otherwise, I cannot play this game if G and H do not commute, and I have both strings at the same time. Okay? But the important thing is that these strings can be deformed and can be moved, and the state is the same state, doesn't change. So this is why I put this in a very particular location, but I could decide any other, and it's the same state, the same object, the same mathematical object. So these strings are not localized in any place. Okay, now properties. Some of these ones are not trivial to prove, some are. Okay, so this one is. So in principle, if I change the group elements, I could have different states or the same state. There is a clear way in which I can modify this. And it's now take your favorite group element and change your tensor by this other tensor. You are not doing anything because it's the same object. But if you do that, or let's put K instead of, because I use already J, put K. K minus 1, K minus 1. If you do that, in this picture, you obtain the same type of state, but with different objects. And the objects, so if you do that, you obtain, and you start with this state, you obtain this state. So G goes to K minus 1, and H goes to KH, K minus 1. But since I'm not doing anything at all, because these two things are equal, these two states must be equal. Okay? Okay, so essentially, and I call a pair of group elements to be in the same pair conjugacy class if and only if there exists a K, that this is true. Okay? Of course, for the single one, this is just the conjugacy class. But this is stronger that this being the same conjugacy class than that, and this being the same conjugacy class as that, because the K is the same for both. Okay? That's why we call it pair conjugacy classes. Okay? K is the same for both. But the key thing is that this is all the freedom. So states in different conjugacy classes are orthogonal between themselves. So they are different states. So they are orthogonal. So the number of ground states in the parent Hamiltonian will be given in the end by the different type of pair conjugacy classes we have. So, okay? But for that, we have to show that all these objects are ground states of the parent Hamiltonian. And this is nice. The proof is trivial once we know that we can move the strings. Maybe I postpone that because I think, yeah. Let me, okay, leave it for now, because I think in the presentation I have, in the last part, probably I do have pictures with that, and it's easier to do with pictures. But the philosophy is the following. So let me do it with hands first. So imagine I have a term in the parent Hamiltonian, for instance, acting on that placket, on this placket here. This placket is not touched, so there is no string crossing the placket inside. So the parent Hamiltonian will annihilate everything which is the usual tensors here and any boundary condition. I do have the usual tensor here and some boundary condition, so I get 0. So that part is okay. But what happens if I consider a placket, for instance, this one here? This one is of different form. I have a G here, a G here, a H here, a H here. Is this 0 or not? Then what I do is, okay, I take this string and move it out of the placket. I take this string, move it out of the placket. I can do that because, as I showed before, this string can be moved. And suddenly, in this placket, there is no string anymore. So I get another 0 there. So precisely because these strings are delocalized, these objects also annihilate the Hamiltonian and also are ground states then. Okay? Okay, by the very same reason, all these objects are locally indistinguishable in a sense, no? Because for any local operation I put, the difference which are the strings can be put out of that. Okay, but this I will write now in a second. So one can prove that these objects are locally indistinguishable. This means that even if they are orthogonal, for any contractible region in the torus, so this means that for any R which is contractible or simply connected, the radio density matrix is the same. So the radio density states of rho of GH is equal for all of them. For all. So for every contractible region, all these ground states have the very same reduced state. And therefore, all the properties are indistinguishable there. The same object. Okay, so even if they are orthogonal. So in a sense, the reason they are orthogonal is a global reason, because locally they are totally indistinguishable. And this is what is called the reason being topological, is because this implies that there is nothing like a local order parameter. A local order parameter is a local observable that allows to distinguish between the different ground states. For instance, if you take a ferromagnet, the Ising model, the ground state can be all spins up, all spins down. But just by measuring a single spin, which is the magnetization, you can decide if it's one or is the other. These things do not occur here, because in all local regions, they are indistinguishable. So this is why they are called topological. Okay, so that's another thing. And okay, that's more difficult to show that they expand the ground state, that exactly the ground space is exactly the set of all states belonging to different pair conjugacy classes. So there is a degeneracy, which is finite. Okay, and this is why they are good candidates for quantum memories, because we have a quantum system, which is the set of ground states, that is only distinguishable globally. So local sources of noise, in principle, should not affect it much, because the difference is only detected globally. That's why the idea is behind. Okay. Okay, and then, since we talk about the area law, usual topological orders come with a correction to the area law, which is additive, meaning that the area law of a region is case like a constant times the area minus some additive correction, which is called the topological entropy. And for these examples, it's easy to show that this is the case. Okay, but that's a bit more. Okay, one can generalize what I said for groups to other algebraic structures, like Hopf algebras, Wychoff algebras, etc. For this example, by hand. Yes. That's as easy as this. So the only thing which is not easy is the proof of the completeness. Also, these two things. So the only thing which is which is not really. Okay, some things are easy, some are a bit less easy. The only thing which is requires some work, at least, is this part. Okay. As I say, one can generalize beyond groups to more complex types of topological order by going to generalization of groups, different. And okay, the key property is again some sort of pulling through equation, but now of course these objects are what are called matrix product operator representations of the corresponding algebraic structure. Something simply. Okay, so that's.
Algebra structure. I mean, here you do have no algebra. Per unit or.
No, what I mean is that here so far I define a state for every non-abelian or abelian doesn't matter finite group. But I can define another state, which is a tensor, a PEPS, a tensor network state, also starting from any finite C star Hopf algebra or any finite C star Hopf algebra in a similar way, I would say. But for there, you need to be more careful about things like exactly how you define. Because, for instance, the key thing, so for instance, if you want, this object is just the coproduct of the Hard integral of the group algebra. For Hopf algebra, you can do exactly the same. For Hopf algebra, we have to be more careful because it's not the Hard integral what enters, it's what is called the Markov trace. Okay, the antipode is this role here. Here, in general, you should put things related to the antipode in this part. But so essentially, this is related to the coproduct up to an antipode of the Hard integral of the group. And this is true for, up to Hopf algebra. It's the same philosophy. With C star with Hopf is subtle because it's not the Hard integral; it's another integral. What is called the Markov trace. What enters.
You get any minimal if you put in, I don't know, UQ, SU?
It's a very good question. So far we have only recovered essentially what is known. But it's open whether one get new things. No, I mean you can maybe try to leave. Yeah, okay, I don't know. Yes. So far, let's put this way, we didn't get anything new. But we just recover everything which is known with this language. This we did. Yes. Of course, obtaining something new is always harder. But okay, good. Maybe there is nothing new. I mean, that's okay, good. Any other question? Okay. Let's see. So for now, I will leave that, and now I will, in the next half an hour at most, I go briefly, very briefly, about the different models of quantum computation, and more or less sketch how in all those models there is something related to the spectral gap behind. Okay, let's start maybe in the original one. So this will be very sketchy. So okay, so the standard model of quantum computation is a model of gate. Okay, let's forget about the really formal way of defining quantum computation via quantum Turing machines, as Bernstein and Bakhtirani did in 1993, but really models are more like the one can touch. So the standard one is the model of gates, in which somehow now that we know our tensor network picture, so a unitary matrix between, let's say, a system C2 times C2 and another, this is the input, and this is the output, C2 times C2, and this is unitary. Okay? Now we know with our tensor network notation that I can write any unitary acting on 2 qubits, like that kind of diagram. So now a quantum circuit is something, okay, I will write it in 1D, but in general it's more like it's a 2D thing. But let me write it in 1D because, so I have one layer, then I apply another layer of unitaries, then I apply another layer, and so on and so forth. Okay. And then this, you need a U1, U2, U3, etc., U4. Okay, so that's, the system is usually initialized in all zeros. Etc. And this state is the output of, I start with all zeros, I apply these unitaries. Of course, if I put them together, it's tensor product by the juxtaposition rule. So I apply this, then that, etc. So this is the state, this is the state which is the output of the computation. And in this output state, we do a measurement. And then the algorithm is to decide which are these gates. Okay, that they have to put there. That's it. Because the quantum Fourier transform is selecting very particular gates. And this is the key subroutine of Shor's factoring algorithm. And it's just a particular way of selecting those gates that implement like a discrete Fourier transform on the coefficients. Okay, so that's the standard gate model. This is the gate model. And if you go to a standard book of quantum computing, like Nielsen Chuang, this is what you find there. Okay? Good. Okay. This has nothing to do with gaps. Okay, that's the standard one. Now I'll go to other models. Okay, so that's. So now what happens is that it happens that many interesting computations or interesting problems in particular NP-hard ones can be seen as are obtaining ground states, ground energies are obtaining. So this can be reduced to obtain the ground state energy of a local Hamiltonian. And then somehow then this opens a new type of ways of obtaining quantum computation. In many cases it's universal, it's as powerful as this, because now the problem to solve is just simply to find the minimum in psi of psi h psi. So we know that if the Hamiltonian is gapped and has some geometric locality, maybe it's enough to do this minimization with tensor networks. And indeed, doing that is what is called quantum-inspired algorithms, because it's classical, but it's inspired by quantum mechanics, simply because essentially we are using tensor networks as a proxy approximation of all states that are relevant. It's more or less now all these startups, like maybe Multiverse, which is very famous here, that are doing quantum computing. Nowadays, what they are doing is really quantum-inspired algorithms, because there are no quantum computers nowadays that are powerful enough. But they do know very good algorithms of tensor networks that can help solving things that maybe otherwise you cannot do. Okay? But this also then inspires other models of computation. And one is the adiabatic quantum computation. And this is interesting. So what you do is you have your, let's call this HT. No, it's bad name. H1. H1. So it's the target Hamiltonian. So we have a target Hamiltonian, but we construct H0, which is a trivial Hamiltonian. With a trivial ground state. Okay, for instance, the sum in I of sigma Ci tensor identity in rest. Okay, so simply in a particular position I do a Pauli set, identity in the rest, and I sum all that, and maybe with a minus. And this is a trivial Hamiltonian, and the ground state is the all zeros, no? With the minus, no? Yes, the all zeros state. It's a product state, so it's trivial. Example, this one, no? This H. Okay, and then the ground state is just the all zero. Okay, so it's a product state. And now, by the way, a local Hamiltonian, a local gapped Hamiltonian, I forgot to say, it's important, the gapped Hamiltonian, with a gap, okay? This has trivially a gap, of course, gap of 1, indeed, it's trivial. And now what we do is we find a path that interpolates between H0 and H1. Yes?
From the physics point of view, it's not really a trivial ground state. It's that the ground state is very easy to present. So
okay.
It's easy from the point of view of physics or the system in which you are implementing this.
Okay, okay.
So it's not so much because reality is such a loaded word.
Okay.
It's something that is easy to prepare.
Okay.
From the point of view of physics.
Easy to prepare. Perfect. Good. Okay. Exactly. That this is a problem you want. The finding the ground state of this Hamiltonian exactly is a problem you know how to solve. Exactly. So you can start here. Exactly. You are totally right. Exactly. Yes. Trivial in the sense of the difficulty of the problem, which is preparing the ground state. Exactly. Yes. 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 Okay. Okay. Good. That's totally right. Something that can be efficiently prepared, and that the Hamiltonian can be efficiently engineered. Okay. And now what you do is you change the interactions from this Hamiltonian that you know how to engineer when you start in the ground state, let's call it psi naught. And now what you do is you change the interaction slow enough. And now essentially you do this path, and then you change the, if you want this goes from 0 to 1, you rescale time in such a way that the time it takes to go from 0 to 1 scales like the time, and now path, and do it slowly using time in time t, and that's the important thing, which is polynomial in the inverse of the minimal of the gaps of h lambda in lambda. So H0 is gapped, H1 is gapped. You interpolate. And the key thing is you must find an interpolation in which the minimal gap, so if I plot, this is lambda, and this is the gap. I start here, and I can go down. This minimal gap is what controls the time. So the inverse of that. So I must be sure that this, if I want an algorithm which works in polynomial time with the system size, I must guarantee that this cannot be smaller than something polynomial, or inverse polynomial in the system size. Okay, that's the efficiency. Okay, so, and there is a particular theorem that I can write by Stefan Teufel, in which, okay, there is a concrete bound of t in terms of these gaps of course, also the derivatives, so the norms of the derivatives of the path, so the path must be sufficiently smooth, and the gap. Okay, so there's a formula that is a bound on this T, particular formula. Okay, but that's, I don't know if it's that important. Someone is interested, I can point you to the reference.
The game is to try to find this H lambda?
Exactly. The game is to find H lambda so that you have a control on the on the gap of all the paths, in particular the minimal one. And if you want to prove that your algorithm converges in polynomial time or solves the point in polynomial time, you must guarantee that the inverse of this gap grows at most polynomial with the system size. That's the So this is the adiabatic algorithm, and of course, in this case, it's crystal clear that the key thing is being able to estimate gaps of Hamiltonians. This is locally interacting, this is locally interacting. Normal interpolations are also locally interacting because indeed you need to engineer the whole path in your system because you are doing this physically. Yes?
There must be some distance to the ground state of your object.
Sure.
Ground state that should have that.
Yeah, sure.
That T, right?
Sure. Let me be precise. Yes. Sure. No, sure. The formula is the following if you want. So take H lambda. So physically, exactly what happens is you find H lambda and you assume that it's sufficiently smooth. And then you know that if T is bigger or equal than, I can write the formula, 2 times epsilon times something like, okay, so I have the formula here. Something like some constant, and then is the norm of the derivative. It's not. This is the gap. In 0 plus similar terms. So essentially a function, let's put a function of the norm of the derivative of H lambda, the second derivative of H lambda, and the gap lambda. And the function is a polynomial function. Okay, this is a polynomial function on those objects. And then what you do, I mean, you do, and of course, the evolution you are doing, so you are changing the time like that, so you are doing this evolution, no? So of course you are changing, H sub t. So you are changing the Hamiltonian with time. Okay, this is the rescaled Hamiltonian, let's put tilde, it's the rescaled Hamiltonian, in which you use that time. So this is the time evolution, and you start with psi naught. Then, after time t, the final state, the distance of this state minus psi 1, which is the target state, is less than epsilon. So that's the. Okay, this is a rigorous proof of the adiabatic theorem in this context. I don't know really what is. There are several adiabatic theorems. Some proofs are not very rigorous. Some are. I don't know really.
No, the thesis proofs are not rigorous.
Yeah.
They have to do with the average energy.
Yeah. So this theorem, I think, is due to Stefan Teufel in Tübingen, or a version of it at least. Okay, I took it from some lecture notes of Andrew Childs. I didn't go to the original paper, but okay. So that's okay. So that's maybe I did this already. Okay, so that's the exact result, saying that and exactly this function is 1 over gamma, and it's a polynomial. 1 over the gap, of course. Oh, this is the derivative as a function of lambda. The derivative as a function of lambda, the second derivative as a function of lambda. So, because, I mean, this path should be smooth.
Yeah. The fact that it has to be scaled should be by the dimensional argument. You need to have ratios, or the first one with second one with gamma lambda.
Yes.
And the roots of that.
Yes, I can write, if you want, I can write the exact formula, but it's a bit, yes. I mean, simply that. Philosophically, I mean, there is a concrete formula, but it's a bit long, involving all these type of terms. Yeah, exactly. Simply tells that exactly. If you control the gap to be polynomially, the gaps to be at most polynomially small or larger, then the scaling with time is 1 over epsilon if the error is epsilon, and this polynomial in time, or polynomial in n. That's the. Okay, so that's probably the most clear computation model in which one needs spectral gaps. The other one is we already commented, this dissipative quantum computation that I will not comment more. In which the solution is the fixed point of a local Limbladian, and then again the time it converges to the fixed point, which is controlled by the gap of the Limbladian or the MLSA constant, gives me the time it takes the problem to be solved. And again, the scaling with the system size give me whether the algorithm is polytime, x-time, lo que sea, ¿no? Okay. Another model of quantum computation, which is very interesting, is variational quantum algorithms. And this is interesting because it's very similar to what we do with tensor networks. Now we would like to minimize psi of psi h psi. And now with tensor networks, we say, okay, we restrict ourselves to states here which are tensor networks. Good. Variational quantum algorithm is really the same, but now we reduce to the case in which psi is the output of a polydept quantum circuit. And this is exactly what you do. What you do is the following. So you have this set of states parameterized by the gates that construct the state, by the quantum circuit, by these gates. Once you construct the state, and you construct it in a quantum computer, you measure the energy in the quantum computer, and you use this information to improve the state. So for instance, from obtaining this, you can obtain also information on the gradient and do some sort of gradient descent over this function, because this is just a function of psi. And psi is parameterized by the gates of the circuit. And the only difference why this is classical and this is not is because these states, even they can be described classically. You can describe classically because you just describe the gates. In order to compute that, which is the key information, the energy, in order to update and improve your search on the family to get the minimum, for this you need a quantum computer. Because doing these estimates when this is the output of a polydept quantum circuit, there's no classical computer that can do that. But in a quantum computer, it's easy. You construct this state and you measure the energy. And that's it. So this is kind of a hybrid classical quantum. There is a quantum part, which is just measuring that. And then there is a classical optimizer, very similar as people do in machine learning or in other places. There is a nonlinear function, and you want to minimize it. And the quantum computer is just to evaluate the function. And the rest is just as any other nonlinear minimizer problem. Okay, so that's good. So this is variational quantum algorithms. And again, the same as with tensor networks, many of these, in order to analyze many of those classical minimizers, maybe one needs the classical analogs, which are previous, of course, to some of the results we have in here. Maybe one can define some sort of semi-group there and try to estimate convergence time and all these things, but that's a different story. Okay, so this is now this is classical minimization. What else? Now, two other that are really very much connected to tensor networks. Two other models. Related to tensor networks. And of course, since tensor networks very much related to the gap, because they are exactly the models for ground states of gap Hamiltonians, again, the gap enters there. So one is measurement-based quantum computation. Okay, here, one constructs a resource state, which is two-dimensional. Okay, there are several resource states, but the original one is the 2D cluster state. I forgot to say the origins of many of those things, but okay, you can see these things in reviews. I think adiabatic quantum computation probably is originally to Eddie Fari and others. Maybe the variational quantum algorithms too, by this variational quantum eigensolver. Dissipative quantum computation, I gave the credit to Chirac, Verstete and Wolf. Measurement-based quantum computation is due to Briegel and Rausendorf. Okay, I think now I give credit to everyone. So the 2D cluster state, which is a PEPS. It's a PEPS in which the tensor, this AV of the PEPS, is the same in all. And is the following is 0, 0, 0 plus plus. I will write now what things are, sorry, 1, 1, 1, minus, minus, okay? Okay, for those, and that's a PEPS, okay? So this is a PEPS defined by this tensor. What does this mean? Okay, this, of course, as a map, this is a map from, okay, let me write, okay, let me, okay, yeah. From C2 to the 4 to C2, okay? Remember that these vertex maps were mapped from CD tensor 4 to CD, in this case, both are 2. And now I have to define a basis here. This simply means this, like that, sorry. The state plus is 1 over the square root of 2, 0 plus 1. And the state minus is 1 over the square root of 2, 0 minus 1. And when I put things together like 0, 0 plus plus, what I mean is 0 tensor plus tensor plus, okay? And the same with the minus. Okay, so that's the notation. Okay, so this, as we say, every matrix, and this is a matrix, a linear operator, we can write in terms of Hertz and Brass of the corresponding basis. This object is a bra, is exactly that object. I can expand on the basis here, the same with that. So this is the tensor, and this is a rank 1 object as a map from here to here. It's a rank 2 matrix, and that's the expression. So if I put this vertex tensor everywhere, the corresponding PEPS is called the 2D cluster state. And it has very nice properties. So we construct the result state. Okay, and now once we have it, what we do, so we have like, this is the idea. Now we start to measure qubit by qubit. So we measure here. Depending on the result of the measurement, we do a measurement here. Depending on the result of the measurement, we do a measurement here, and so on and so forth. And we do this row by row, sequentially. And at the end, we obtain the result of the computation. Okay, this is. And then it's nice. So what is happening is that by doing these measurements, in these virtuous degrees of freedom associated to these lines, selecting what measurements to do, implement quantum gates here, 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 and here, up to errors that are correctable. So doing these measurements is implementing a quantum computation in this virtual degree of freedom of the tensor network. And therefore, this is the way they can show, okay, one way one can show that this model is as powerful as the gate model. But it's important that you have to construct a particular concrete state, and once you have it, all you have to do is measurements which are local, single site measurements, but in a sequential way. Okay, so that's this. And then topological quantum computation. And that's much more sophisticated. Okay, so now this is one of these topological PEPs. But for instance, the simplest one is for the group S3. This must be a non-abelian group. So we have shown before which is the description of the ground state. But now you need the first excitation, so the elementary excitation. So elements which are eigenvectors to the, not to the smallest eigenvalue, but to the next to the smallest. Okay? And they are described by strings, but instead of closed strings, they are open strings. So we have G, 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 for instance. I can deform the string, but what I cannot change is the two plaquettes where it touches at the end. Yes.
So G isometric and topological is the same.
Sorry. Yes.
G isometric and same topological is the same.
No, not really. You have models which are topological beyond groups, of course, and then indeed most of the so like the Fibonacci anions, for instance, things like that, they are beyond groups, but then they come from Wychow algebras. So you need these generalizations to include everything. But yeah. Okay, so and now one can show that the excitations that say to live here and here behave like quasi-particles, behave like particles. And when you interchange them, you braid them, they behave, they are not bosons or fermions, they behave in a very weird way. And in particular, you can implement gates, you can implement unitary transformations like that. So instead, the topological quantum computation is you create excitations and you braid them. I think I have a picture later. In the sense that this is just, you can see this as one thing and one string in between, no? This and one string of G's. You have another string. And then you just pass this through that and go back. And when you do these things, something happens. Okay? And one can show that by doing that, you can also do universal quantum computation. Okay? And this idea, I think, goes back to Kitaev in this very influential paper from the early 2000s. But okay, I will not say more about that. Okay, so I will go then to the final part. Any questions, by the way, so far about this? I know it was very sketchy, but at least that you had an idea that many of the things that I told you so far really connect with the very different models of quantum computation.
with the quantum computers you have now? What this can be?
It's a very good question. It's not clear which is the best. So many people are going now for this variational, but indeed, essentially, all the algorithms that really have been doing something very important, let's say, like these quantum supremacy algorithms, they go direct to the gate model. So, but again, correct me if you. Okay, that's true. There are some people that, yeah, exactly. Some other companies that are going for the adiabatic. That's true, like D-Wave. Yeah. Or the.
Some dispute or they actually do that.
Okay. There, essentially, I was thinking more on IBM and Google, and probably also Amazon. Yes, and all this. But they are mostly gate-based in the end. No? But it's true that there's the D-Wave, maybe others. I mean, I also lost track of all the actors here, but yeah, D-Wave always went for the adiabatic, but they were always very controversial because in principle their machines had quite a lot of noise, and it's not clear exactly if they are doing quantum or not, but I don't know. But I don't know. I mean, I guess people are exploring a lot of variational quantum algorithms nowadays. I don't know if they already got any major result with that. Or the big results that come to my mind, like supremacy and other things. Correct me if I'm wrong. I think they came already from just simply from the gate model. But yeah, let's see what the future says.
There was an attempt by Microsoft.
There was a much publicized attempt by Microsoft at something that was more topological. But they are kind of walking away from those claims because they haven't realized them.
Yeah, I think probably there was a lot of expectation for topological quantum computing because it's supposed to be much more robust. But yeah, it seems that they were having a lot of experimental problems to get these things happening, and then I don't know which is the state of the art currently in that sense. Yeah. Okay. Yes. In any case, you have here experts. You can ask them. So let's go to the final part. Is this correcting? Okay. Okay, good. Which somehow what really happens, or I mean, one is people are using topological order or topological models as memories. For instance, like surface code, some of the codes that people use, even in practice, in quantum computers, to trying to understand how to scale error correcting codes and these things. So it's something that really people use. And then, at some point there was a question whether topological order could give the highest degree of correction, which is self-correction. Because now error correcting codes, you need to do things actively. You have to measure, you have to correct based on the measurements. These measurements create more noise, and then you have all these type of things. So if the memory were self-correcting, so you had to do nothing to correct, it would be very nice. And in principle, okay, this was a question, and there was a very important paper long ago already. Maybe I forgot, Dennis, Kitaev, Preskill, maybe, I don't know. Early 2000s, they show that self-correcting topological quantum memories exist in 4 dimensions. But of course, it's very difficult to realize a quantum computer in 4 dimensions. So then the question became whether this obviously exists in 2D or in 3D. 2D would be optimal because most quantum computers nowadays are 2-dimensional. They are just cheap. But already 3D would be nice. The search for this 3D self-correction motivated Zhongwan Ha in his thesis at Caltech to discover a new class of phases of matter, which are called now fractons. Though still the problem is not solved, but I mean, open a very new line of research of new exotic quantum phases of matter in 3D. But we here will focus on the simplest 2D case. In the 2D case, everyone believes now, since long, that these things do not exist, and our results go in that direction, to formalize rigorously that belief. Okay, so that's, and the idea is that I will try to, here all these several ideas are come together in a nice way, and then maybe this helps you to fix things in your mind from the previous lectures. Okay, so this is the big question. This is the belief. And now with the self-correction. Okay, so the idea is you have a physical system that encodes quantum information, and it should allow it for a macroscopic period of time, meaning that the decoherence time, so that the time it takes for the information to be destroyed, grows polynomially with the system size. In the sense, if I want larger decoherence time, I just increase the size of the system. Okay. In general, self-correction talk about thermal noise, and this is what we will do also here. But the important thing is without active error correction. So just you don't do anything at all in the system. Okay, in the classical case, there is a self-correction exists, and it's just a 2D ferromagnetic Ising model. Okay, this is thermally stable, but unfortunately, it's not stable under perturbations, because a tiny magnetic field breaks the degeneracy between all up and all down, and then, okay, even if it's nice, but okay, it's not nice in the sense that it's not stable under perturbations. Maybe for classical regimes, this perturbation is not that a problem because one can do things exactly in a sense, but in quantum mechanics, one must allow for small perturbations because you never do the things the exact way you want to do. So the fact that this is not stable under perturbations will happen the same if we have a local order parameter, because you do a tiny perturbation in this local order parameter, which is the magnetization here. So we need, if a quantum self-correction exists, we need to ask also for stability. Okay. So one needs quantum systems that have degenerate ground states, no local order parameters, and stable under perturbation. This immediately tells you, okay, you should look in topological order, because the only quantum systems that are known to be mathematically proven stable under perturbation and topologically ordered models. Systems with no local order parameter, essentially by definition, are topologically ordered models. And we know that topological ordered models have degenerate ground states, as I showed you before. So we have to go here. Okay, this is a very nice picture. In Quantum Magazine, they made a nice article about the classification of topological phases, and they have a super nice picture that I took. So the article is very nice, so if you're interested. Okay, so let me go fast through this, because this more or less is what I showed before. So we have this gauge degree of freedom, and this is what I say, that these loops one can deform. This is what I just showed in the blackboard. This is the fact that that these objects are ground states. This is what I told you that I can show now. No? So I would like to show that this state with a string is also a ground state. So if I add my parent Hamiltonian here, nothing happens. If I add my parent Hamiltonian here, I have this string, but I can move the string. I deform it, and suddenly the string is no longer here. So essentially, all the terms in the parent Hamiltonian are annihilated, because these are annihilated because by definition the parent Hamiltonian, and these are annihilated because this string I can pull out of the range of my operator. And okay, all these properties we know that we have a degeneracy of the ground state. we know that all ground states are indistinguishably locally, as I showed you before, or told you before. And there is this result by Bravi, Hastings, and Michalakis showing that topological ordered systems are stable under perturbation. Okay, so that's... Okay, so we'll then focus on these G isometric pairs that I told you before. That is exactly, as I said, Kitaev's, what are called Kitaev's quantum double models. And for the case of the group equals C2 is the toric code. Okay, I said all those things with words, but now they are written down here. And therefore, these are candidates to be good quantum memories. And the question is if they are not just good quantum memories, but they are also self-correcting quantum memories, which is much stronger. Okay. Okay, so that's more or less the setup. Any questions before I go into the meat? So I was just repeating a bit the things I did before. Okay, good. Let's go. Okay, so we take our two-dimensional topological model with some Hamiltonian, which is topological. So for our examples, the parent Hamiltonian of the PEPs associated to these G isometric PEPs. Okay, this what I define myself as Kitaev quantum double models of a group. We take this Hamiltonian, which is made out of commuting terms. Remember that I proved already that these terms commute. I proved it in 1D, but the proof in 2D is the same. And now we assume thermal noise in some coupling limit, and there is some construction by Davis from the 70s that gives us a particular form for a Lindbladian, which is the noise model associated to thermal noise. Okay, for this particular Hamiltonian, I get one Lindbladian. This Lindbladian is also local. But even if the terms of the Hamiltonian commute, the Lindbladian terms do not commute. Okay, so this object is not commuting. And then I initialize in some element in my ground space, so some element in which I have my information encoded. And this is the evolution at time t. And then I would like to know how long does it take to reach rho infinity. Rho infinity for the thermal noise is exactly the thermal state. Okay. Okay. I didn't normalize it. It is divided by the trace. Okay, the thermal state. In the thermal state, the contribution, because it's the exponential of minus beta h top, the contribution. So, I mean, let me write it, maybe it's better. So, all the information is in the ground space is gone because all the ground space is treated equally there, no? So, if H is essentially the lambda 0 for the projector onto the ground space plus lambda 1, P1, etc. No? Now, if I do e to the minus beta h, essentially all elements in the ground space appears via the projector onto the ground space. And therefore, which ground state I started with is totally washed out. Okay? But the information was encoded precisely in which ground state I was starting. So once I'm in the thermal state, all information in the memory is gone. Okay? So the information is lost. So essentially, in order to give a bound in the memory time, one can try then to estimate the gap in this Lindbladian. So if we show that the gap is bounded below by something that depends on temperature but is independent of the system size, then we have bounds on the mixing time, on the convergence time. Okay? The big open question, so we'll talk only about the gap, is whether one can upgrade the results to MLSA constants. And this we don't know. Okay? So here we'll prove this result, that these Lindbladians are gapped. Since all the results we have to upgrade from gap to MLSI do not apply to these models. Okay, so which was known before. So there is a paper, 2007, from Aliki, Fanes, and Norodeki, in which they proved exactly that, but only for the toric code. So for the group being C2. Then, Komar, Lando Cardinal, and Teme, 2016, prove the same for abelian models. And now, okay, we treated for the first time the non-abelian case. The non-abelian case is interesting because in order to have universal quantum computation, you need non-abelian groups. And then we prove the same result, okay, different bounds, but same result, that also for the non-abelian case, for all quantum double models, for any group, the same is true. Okay, so there is a nice corollary, is that from this one obtains that the thermal state of any quantum double model can be constructed efficiently in polytime, which is, I think, is nice, at any temperature. Okay. Okay, so this is the result. So how do we prove this? So now, with all the things in the course, you should say, oh, I know what you should do. You consider, so the idea is, okay, you have the Limbladian, you need to find a nice Hamiltonian and try to estimate the gap of that Hamiltonian, and then maybe construct a tensor network. Okay, so let's see how these things enter. Okay, so consider the thermal state. Now with the thermal state, we want to, this is a state which is not pure. We want to find it like a pure state. And this is something which is called the thermophile double, which is simply when you have an operator, because this state is an operator, you have like Ketz and Brass. So you do a partial transposition and you convert Brass to Ketz. You double the system, and then you get a pure state. Okay, that's, in this case, you can even see this in a way like a purification, but this is just an algebraic manipulation. So you take some mixed state. This is like a matrix, and you see the matrix as a big vector. That's it. This is what we are doing. Okay? Yes.
So, an abstract operation, a tensor product.
Yeah. Okay. Yeah. Okay. This is just very vague. So essentially, this object here, you simply interpret. So so this object belongs to MD tensor system size, no? And now I see this MD, I identify with CD squared. This is what I'm doing. That's it. That's all I'm doing. And therefore now it's a vector. This is all I'm doing. Okay? Yes?
Because you mentioned the space spring, it's actually saying that any mixed state can be presented as a pure state by going to a larger state, with the space spring dilation that David mentioned. So what happens is that you're always assured that this exists. The size of the increase depends. The size of the increase is finite for finite dimensional spaces, and this is the canonical way of doing purification for all absolutely all states.
But this is not a purification. So this is this.
Yeah, it is a size purification as well. It's a pure representation of the mixed state. The partial trace gives you actually the mixed state.
Yes. Okay. Yes. Okay. Okay. In this way, one can do that by changing a bit the temperature. But I mean, I don't need that yet. But that's true. Okay. One can think in that case this as a purification. But this is much simpler. It's simply just looking at that as a vector space. That's it. What I'm doing. So I'm not. Yes. So because I mean, in principle, if you want a purification, you want some psi, so that psi trace of the environment is the original state. That is what you want. I'm not for the way we do, we could get it by, I think, putting beta to 2 beta or something like that. But this is, I don't want that. All you just need is this. It's very simple. Okay, is that. Okay, so So now I have a pure state. And then one nice observation. Oh, but the one is this is a PEPS. This is a PEPS. Okay. So this pure state is a PEPS. And this is a PEPS because the parent Hamiltonian is made out of commuting terms. So you have a parent Hamiltonian method of commuting terms. The thermal state is a PEPS, exact PEPS, not an approximate PEPS, exact PEPS, exact. Okay, there is no approximation. Okay, if this is method of commuting terms, this is exact. So this is an exact PEPS. And now the key thing is we have this Limbladian, and now in the PEPS, there is another Hamiltonian, which is the parent Hamiltonian of the PEPS. One can show is that the gap of the Limbladian is the same, of two constants, to the gap of the parent Hamiltonian of the PEPS. And this is the way in which you go from the gap of the Limbladian to the gap of another Hamiltonian. This Hamiltonian has nothing to do, a priori, with this topologically ordered Hamiltonian. This is the parent Hamiltonian of the PEPS, which is the thermophile double associated to the thermal state of that Hamiltonian. Okay? So essentially, we start with some Hamiltonian, we construct the thermal state. This Hamiltonian defines some Limbladian via noise. And now this Limbladian allows me to define a different Hamiltonian. That is the one I care for the gap, which is not the original one. Okay? For instance, this has commuting terms, and therefore trivially has a gap of at least order 1. And these terms do not commute. And it's not clear at all whether it has a gap or not. Okay? So it's a different thing. But this is the philosophy. No? We want to analyze a Limbladian, we construct a Hamiltonian, and even if this Limbladian comes from some Hamiltonian, this Hamiltonian is a different one. And that's the one we have to analyze. Okay, so the problem boils down to estimate the gap of the parent Hamiltonian of a PEPS, which is this one. The bad news, as I told you before, is that we proved some years ago that even for parent Hamiltonians of PEPS, the spectral gap in general is undecidable. So one cannot hope to have a general recipe that works for all parent Hamiltonians of all PEPS. Okay, then what we will try to show is to find sufficient conditions for the gap of the parent Hamiltonian of a PEPS and prove that this, we are lucky enough, that this one fulfills those sufficient conditions. Okay, this is outside of the undecidable family. Okay, that's the goal. Okay, so the solution comes via an idea, which is kind of an holographic idea, bulk boundary correspondence, that goes back to this paper by Ignacio, Didier, Norbert, and Frank, and in which we somehow they had a very nice idea, and they give numerical evidence, and then we managed to prove some of their results rigorously. So, okay, so which is the boundary state of a PEPS? Okay, let's see if these pictures are good enough. Okay, so we have a PEPS. A PEPS is an object like that. And this is a region, and I leave this boundary open, okay? So I'm not closing the boundaries. So the boundaries are open. So this object has a part in the bulk, which are these blue legs, and a part in the boundary, which are these black legs. The blue ones are physical, the black are virtual. So now we do this object, and I see this object as a linear map from the black to the blue. And this is this map gamma R that I told you before, no? From virtual to physical. And you consider this map times the adjoint map. So I take this map from virtual to physical, and then I put on top the adjoint map. So I have this gamma R daga. That's what I'm doing. Okay? So this is a linear map from the boundary to the boundary. Okay? Which is positive. The boundary is clearly one-dimensional. So, okay, if we normalize it to trace one, this is a mixed state in the boundary. Because a positive operator in a one-dimensional object. And this is called the boundary state. Okay? So it's a mixed state, meaning that it's not pure, which is one-dimensional that lives in the virtual degrees of freedom at the boundary. And it has nice properties. It defines the parent Hamiltonian of the state. If I have time, I will show you how. probably I do have time. And it also mediates the correlations in the system. The correlations in the systems can be deduced from properties of this mixed state. Let me skip this because I have time. Okay, maybe I will show how to define the parent Hamiltonian based on this boundary state. Okay, the boundary state, in 1D, of course, because painting in 2D is hard. The boundary state in 1D is that, no? I have boundary, bulk, boundary, no? So that's a map from these two to these two. And now the parent Hamiltonian is, remember, the very same we did for G isometric, but now we have to plug here in between the inverse of the boundary state. And okay, this is an orthogonal projector. This is clear that this self-adjoint is obvious. This is something dagger, and I put in something positive here. So this is clearly self-adjoint. And this is a projector. If I apply this to itself, in the middle, I have that cancels this. And we get the same thing. So it's an orthogonal projector. That's clear. And what happens if I apply this object to the matrix product state, or the PEPs, no? The matrix product state? Then it's clear, no? I here obtain again the boundary state, which cancels with that. And I get the same state. So this object stabilizes the state, so the parent Hamiltonian is identity minus that. Okay. So there is a way to write the parent Hamiltonian from the tensors themselves and the boundary state. Okay. And that's general for 2D, 3D, and ED. Okay, so how do we prove or give characterizations or sufficient conditions, as you said, of the spectral graph via boundary state? Okay, so which is the conjecture? In this very breakthrough paper from 2013, they show the following. They conjecture that the parent Hamiltonian of the PEPs is gapped if and only if the boundary state is the Gibbs's thermal state, is the thermal state of a short-range Hamiltonian. So if this boundary state can be written as something like E minus beta H with H local, then the parent Hamiltonian is gapped. The conjecture is an if and only if. As a 1D Hamiltonian, and it is short range. I mean, it can have exponential tails. So exponentially close to local. Yes. I mean, could have exponential tails. Okay. So what we try to do is to prove that. Okay, and there is an intuition why. Why that? More mathematical intuition. Probably some of you know Araki's theorem. Araki proved rigorously in the 60s that there are no quantum thermal phase transitions in one dimension. He proved that the Gibbs state of any finite range, meaning exactly local one-dimensional Hamiltonian, have exponentially decaying correlations. Essentially, it's also believed, in a sense, that gapped systems, so it's proven by Hastings, that gap systems, the ground state of gap systems, have exponential decaying correlations. And it's, okay, even if there are counterexamples, the other implication is also somehow believed with sufficient nice systems. So essentially, the idea is that gap in the Hamiltonian should be the same as exponentially decaying correlations. The correlations are mediated by the boundary state. So maybe all these things say, so maybe if the boundary state is a Gibbs state of a finite range Hamiltonian, Gibbs state meaning thermal state, then okay, maybe this is the reason why you have a gap in the bulk. I think this is more or less the intuition behind this, but they did just numerical test for some systems. Okay. In any case, this is maybe for people that are more familiar to this background. If not, just forget. Simply just, it was conjectured. Okay, so what we prove now, theorem, is now if the boundary state is what we call approximately factorizable, then the Hamiltonian is gapped. And approximately factorizable is that we can write it as the product of two objects. One that acts only non-trivial on AB, an identity on C, and the other that acts only non-trivial on BC, an identity on A. And okay, for a particular notion of distance that I will not write. Okay, this is what we proved. First theorem. So, okay, if the state is exactly factorizable, is an equality, then implies that the Hamiltonian terms commute. And therefore the system is gapped. And then this approximate case reduces to something which is called the martingale condition that Bruno and Nachtergaele introduced in 1995, and he proved that the martingale condition implies gap. And later, in a paper 2018, Angelo Lucci and Michael Castrogiano proved that indeed martingale condition is equivalent to gap. So essentially, this, if you want, we read it as the way to see the martingale condition in the boundary state. And this is indeed a condition we will check at the end in our particular example. And now theorem 2, we prove that Gibbs states of Hamiltonian with fast decaying interactions are approximately factorizable. And these two theorems together somehow prove a version of this conjecture of Firac and company. Okay, so that's more or less the idea. Okay, how do we prove this theorem 2? Okay, this is extremely a huge simplification, but imagine that instead of having a thermal state, the temperature is imaginary. Okay, and you have e to the minus IH. Okay, imagine. Okay, then because h is local, by something which are called Lieb-Robinson bounds, one can show that this evolution can be well approximated by a finite depth quantum circuit. So this is a quantum circuit that approximates this evolution, and then it's clear how to define A, B, and C, so that this is a product of two operators, this operator and that operator. Okay? That's it. So, okay, the problem is that these Lieb-Robinson bounds work for normal times, say for time evolutions, but not for imaginary time, so for thermal states. So we had to prove locality estimates for thermal states in order for this idea to hold also for imaginary times, for temperatures. Okay, that's what we did. Okay. But indeed, the idea is essentially making this work in our context. Okay. So now we can finish the proof. Repeat what I did before, thermal state, thermofield double, which is a PEPS. We prove that the gap of the parent Hamiltonian is essentially the same as the gap of the Lindbladian we're interested in. So we have to estimate the gap of this Hamiltonian. And now we have a way to do that, which is if we can show that the boundary state of this PEPS is approximately factorizable, this Hamiltonian is gapped. And this will be proof. We go for this particular PEPS. We construct explicitly a explicit formula for the boundary state, and we check that is approximately factorizable. And so this is the boundary state of that PEPS is approximately factorizable. End of the proof. That's what finishes the argument. Okay, so that's a bit how all these things come into play. And I think that's it. And thank you. So I have still some time for questions if you want. Sure. One more?
Yes, this one. Because I don't understand why the Newtonian is to commute. The terms of the Newtonian is to commute. Because What would happen if they don't commute? We have a lot of them.
No. What? Sorry, again, can you repeat?
Like, can you elaborate a bit more on the commutativity of the terms of the Hamiltonian?
No, okay, okay. Here, there is nothing. So simply say that the important thing is approximate factorizable, and this simply saying that if this is an equality, the only case in which you can have an equality is if your Hamiltonian already is commuting, and then of course it's gapped. But so it's simply just you can forget about that. There's nothing about this.
I don't know, like
But
model the Hamiltonian with a transverse field. The Hamiltonian is gapped, but
No, exactly.
the
Yes.
terms doesn't commute. So
Yes, of course. Yeah, of course. This all this is done for Hamiltonians without commuting terms. Remember, I mean, the Hamiltonian that has commuting terms is the topological Hamiltonian. But we are applying all this to the parent Hamiltonian of the thermofield double, and these terms do not commute. Of course, if the Hamiltonian terms commute, the gap is trivial. No. Of course, this is for parent Hamiltonians of PEPs with not commuting terms. And we are applying this to the parent Hamiltonian of these PEPs, not to the topological order Hamiltonian, which is the parent Hamiltonian of a different PEPs. Okay, so that's yeah. Any other question about this or about anything about the lectures? I mean, there's no.
Maybe I also
Sure.
about the adiabatic computation. Is there any trial of using another type of condition instead of the distance between the graph state, using, for example, the one you showed, this entropy relative
Yeah.
distance?
Unfortunately, my knowledge of adiabatic computation is super minimal. Maybe someone in the audience can answer. I cannot answer.
Because also there, I was confused by this lambda with infinite gap, with minimum gap. How do you ensure that this gap doesn't close?
I don't know. That's a difficult thing, of course, but because I mean, that's a problem. It's very difficult for an algorithm to know whether it converges in polytime. So for how many quantum algorithms do we have a polytime convergence guarantee? Not that many. And so this is a very difficult question. And in that particular type of computation, this is encoded in giving a bound on that. But of course, this is very hard.
So for self-correcting quantum memories, you assume that you were like not allowed to do anything on the system. So if you allow some local operation or something, can you like improve the lifetime of the memory? Or?
It's a very good question that I also don't know how to answer. Yes. Yeah, so you mean some intermediate regime between self-correcting and fully? It's a very good question. Probably people have done this. I don't know. I also. No, I don't know. So my feeling is that people lost a bit of interest on these self-correcting quantum memories. Now the quantum error correcting interest is going more into other things like LDPC codes and all these things to do active error correction, but trying to get super good codes. Also because, yeah, maybe also these topological systems in the end turn out to be harder to implement than they thought. I don't know. As a mathematician, I like still a lot this question as a fundamental question, but I would say that the interest of the community is probably not anymore that much into that. Okay, so maybe being the last Friday afternoon after so many hours, we can stop now, I think.